Okay, we're going to go and talk about today about volumes again. So volumes, and we're doing this through rotations. And we're going to rotate around an axis. And we can pick the x-axis or the y-axis, and it gives us different shapes. So last time we talked, when we create a volume, we take some type of function. Let's take some type of graph like that. And then we'll stop it here. So it's an upside-down parabola. And we would spin this around in a circular way. We're going to revolve it around the x-axis here. And we're going to spin it in this like clockwise direction here. And you would end up with this shape. Give yourself a mirror. You end up with something like a doorknob. So our goal here is that we are making solids in this most basic possible way. In the physical world, things aren't this perfect. But since we're in high school and calculus is like the peak of high school, but though it's kind of like the bottom of the real world, we're just kind of looking at these on the super basic level. That's why we're just spinning around one axis with one function. If you want to really talk about like 3D images and 3D objects, we could have like 100 formulas, 1,000 formulas, 1,000 functions that we could revolve and spin. And we don't even have to spin a full 360 degrees. We can maybe spin it 10 degrees. You can imagine when you take an actual object and you throw it into a 3D imaging program, it's drawing curves, it's using functions, and every little curve has its own equation. And we're just dealing with one equation and one rotation to make it super easy for us. And we said, when we are spinning objects around, we form a circle here. And in calculus, we're able to cut these circles into slices, an infinitely many set of slices. And the way we find the volume is literally by stacking up these little discs on top of each other. Till we end up with this solid shape. Now, if you want a more accurate disc, you come up with a smaller, like a width. And the smaller the width, the better shape you have. Okay? So very similar to what we did for Riemann's sums. Riemann's sums, we took a curved object and we drew just rectangles because it was a real basic way of looking at it. But then we could approximate what the area underneath the curve was. And if we took smaller rectangles, we would have a better approximation. So our simple shape is a circle. For circles, our equation is pi r squared. And if we multiply by a little bit of width, we end up with a volume. So the idea is this is area times a little bit of width gives us our volume. Or you can say height even. But our height is kind of sideways. So let me draw that as one shape. We take the area, we multiply it by a little bit of width, or you could call it height, and that gives you a solid volume. So we said to find the volume, it was pretty much pi integral r squared with a little bit of x. And in this case, our r was our radius. Let's look at that right now. The radius is actually the f value of my function. It's the height of my function. So it's the integral of f of x and then back to dx. And then we want to go from a to b, from our starting to ending value, from our a to b value. Now today, we're going to move on from very simple solid shapes to what we call washers in math. So today we're going to do washers now. And this is actually what they call it. They call them washers. And the washer is a disc with a hole in it. Okay? Now how do we end up with that hole? That's what we're going to talk about today. And it's actually kind of not that terribly hard. So let's come up with a fairly simple example. If I give us our curved surface on top, and I follow up with a second equation, almost like an upper and a lower bound. So we can say this is my f of x on top, and this is my g of x on bottom. Okay. Now, if I rotate this around the x-axis, spin that around on the x-axis, we end up with a mirror image. And this is gonna, let's see, let's try my best here. Yeah, I could do a little better with that. So we end up with a donut. Okay, this probably needs to wider out. Okay, we end up with this little donut tube. Now, if you remember in geometry, we dealt with area of surfaces and we could cut holes in them. If you remember geometry, if I give you guys a regular circle and ask you to cut a hole in it, let's say the big R was 5 and the small r was 2. How would you find the area of the rest of the circle? The area would be the area of the larger minus the area of the smaller. So we would take the full area, pi r squared, sorry, I should write that in. It would be pi 5 squared minus pi 2 squared. We would just subtract the overall areas. We would use the basic formulas that we already know, and we would try to accommodate our new picture using our formulas that we already know. And we know the area of a solid circle. So to come up with a wholly circle, we would subtract the larger circle minus the smaller circle. And this is essentially what we are going to do here. Since we know how to find the volume equations, remember this is my volume equation for solid shapes. Well, how to end up with two solid shapes? I'm going to take the larger solid shape minus the smaller solid shape. So for this example here, let's go ahead and pretend that this doesn't have a hole. This is just the function f of x. If I spin f of x, we end up with this doorknob looking thing. And that equation is actually quite simple. That's pi r squared. Let me just rewrite it in a nice way. The volume of our larger shape, our outer, use the word outer. The volume of our outer is equal to pi from a to b of f of x, because that's the outer equation, dx. Oh, sorry, squared. Pi r squared. And then our equation of our inner, let's go draw this on the side over here. We said this was g of x. If we spin that around, that's a tube on the inside. So that's going to be pi, volume of the inner, is equal to pi integral from a to b of g of x squared dx. So how do we find the area of, of this donut section right here? Well, we just subtract the outer from the inner. The formula is, so the volume is equal to the volume of the outer minus the volume of the inner. So to write that together, the volume of the outer is pi integral from a to b of f of x squared dx minus pi integral a to b f of x, sorry, not f of x, sorry. The inner equation was g of x squared dx. So this is a very big picture, Now, this formula is a basic rough draft of what we're doing. So I'm going to use some algebra too. Now I'm going to combine this together and some identities for us. So the volume of our washer, do you see how they both have a pi? Let's factor that out. Pi in the front, and we're left with the integral from a to b of f of x squared dx minus the integral of a to b of g of x squared dx. Now, one of our rules for integration is that I can combine if they have the same interval. So they both go from a to b. So I'm going to combine this, make this look a little prettier, like in your book. And I'm going to write them together as f of x squared minus g of x squared. So let's simplify this even more. The volume of a washer, it's pi from a to b of the outer radius squared minus the radius of the inner squared. And this is the basic idea right here. You take the outer function minus the inner function. Now the outer function and inner function, these could rotate because the picture we have here, I'm rotating this way. But for the same example, I could actually rotate along another axis. The same example here. If I took these two functions, call this f and g, and what if I asked you to rotate around 5 up here? So this would actually be spinning up. So this would look like the mirror image. I'll draw this mirror image here. Would look like this going this way, and this line going this way. This would look like almost like a weird vase or a bun cake looking thing. Like a toilet paper roll with like the inside squeezed in. Now for this example, what would be your outer and what would be your inner here? Well, from the axis of rotation, if my axis of rotation is that 5, the outer would actually be g, and the inner would be f. So we actually spin the equation around. And the radius is going to be somewhat different now. So let's come up with the radius of the outer. Let's look at outer radius. Well, the axis of rotation is 5. And if I minus g, this is my outer radius. Okay, let's try that again. It's 5 minus the value g gives you what's left over inside. Now let's say if g was 2, and it's kind of easy when you give yourself examples that work in your head. If g was 2, isn't the radius 5 minus 2 is 3? 5 minus 2 is 3. 5 minus 2 is 3. It's always going to be 3. If this g equation was constantly changing, it doesn't change the fact that it's still 5 minus g. Let's look at the inner radius. Inner radius is 5 minus f. 5 minus f. It's going to be 5 minus f. So it's 5 minus f, 5 minus f, 5 minus f. No matter where you go, the inner radius is still going to be 5 minus fs. Okay, so it's 5 minus f. So that when you're trying to like figure this stuff out in your head, it's always the outer radius minus the inner radius. And specifically, how do I find the radius? Actually draw out the axis of rotation to your radius. And that might help you like connect the dots here. So let's come up with this volume equation for this washer. The equation for your washer, writing on top, is pi integral of outer radius minus inner radius. And we're squaring them separately because they're two actual separate objects. Two actual separate objects. So that's actually just plug in our outer radius, inner radius equation. The volume is pi, integral from A to B, whatever that would be. And the outer radius, just copy the equation. It's 5 minus g of x squared minus, okay, what's the equation of my inner radius? What's the inner radius here? Looking here, my inner radius is 5 minus f of x, close it squared, all multiplied by a little bit of dx to give it a little bit of width. And kind of cool, if you guys want to look at this, remember how we started off on a 2D way of looking at this up here? Didn't we really say it's the outer minus the inner? That's exactly what we do here. We said it's the outer pi r squared minus the inner pi r squared. It's actually the same idea. So once we get that area, we multiply by a little dx, give it a little thickness to that curve, a little bit of dx here. That gives you the volume. Now, this works for pretty much most ideas, rotating around the x-axis. As we transition to rotating around the y-axis, we have to switch our equations around. Because we are no longer dealing with dx, we're dealing with dy. So let's just do one equation here, one example. An example is, if I say y, so my graph is bounded by y is equal to 4, and the equation y is equal to square root of x, between x is 0 and x is 1. So these are going to be easy values to plug in. Let's draw that out. We have a square root graph, which looks like a curve like this. That's my square root of x. And from 0 to 1, the square root of 0 is 0. That's why over here. And the square root of 1 is 1. And my y value, we said, my second value, color that in blue. My 1, 2, 3, 4, 2, 3, 4 up here. Here's 4. And then we have this object here. Okay. This is my weird shape object. And we want to rotate this around the x-axis going this way. Well, what would be my outer radius? Would the 4 be my outer radius, or the square root of x be my outer radius? Looking at the graph, it looks like, well, so remember, you have to like identify this for yourself. Like, if this is my axis of rotation, if this is the middle, well, what's the outer? Is the 4 the outer, or the square root of x outer? And it looks like the 4 is outer. So my outer radius is going to be 4, and my inner radius is going to be square root of x. Now, just to draw this out so you guys can visually kind of see it, if I kind of copy it over, we'd end up with this. That was terrible. Kind of looks like, again, what would you say that looks like? It looks like a cylinder with a half an egg in it. Cylinder, half an egg in it? Yeah. Okay, so we've stick to our basic equation, which is really subtracting 2 volumes, 2 circles from each other, two cylinders. The second one's not really a cylinder, but egg-looking thing. And if we just follow the equation without thinking, it's just a to b. In this case, my a to b was 1 and 0. Volume is pi, so 0 to 1. And then we're going to take our r squared, our larger r, my outer r, minus my inner r. So my outer radius, looking from 4 to 0, 4 minus 0 is just 4. That's my outer radius. My inner radius is going to be the function square root of x minus 0. Well, that's just going to be square root of x. I want to square that. Multiply this out by dx. And that's really the setup. The rest of it is just practicing our integration. And in this case, this would actually be pretty easy. if I continue, v is equal to pi. We can multiply that out. 0 to 1 of 4 squared is 16 minus square root of x squared is just x. And then that integral would be pretty easy. Okay. Let's do the same problem, but this time I'm going to rotate it the other way. We had called this 4. We had a square root here. And we're going to rotate it. I'm just going to pick a value, 5, 6, 7, 7. What if I rotate it up? To draw the mirror image. 1, 2, 3. This is for the inner. And then the graph would look something like that. So this is like, and this looks like a hollow tree stump. Hollow tree stump. So for us to figure out what's what, well, let's figure out what's my inner radius. If this is my axis of rotation, what is my inner radius? Well, the inner radius is from this to this. That's my inner radius. My outer radius is from the axis of rotation to the next function. Now, I'm going to tell you the hint. When I'm subtracting these functions, you always want to go greater to smaller, or up to low, okay, right to left. So since 7 is bigger than 4, we're going to go say 7 minus 4, and that would be the radius. And obviously, 7 minus 4 is 3, and 3 is my radius. The second one, 7 minus the equation, whatever that equation is. This equation, it looks like it's going to be square root of x. So to come up with the function is pi integral from a to b, we'll say 0 to 1 again. And what's the outer radius minus the inner radius? Is outer 2 t's or 1 t? I almost forget that. My brain is not made for spelling. No, that's 1 t. I don't know why I wrote 2 t's. And then inner, for sure that's 2 n's. Outer and inner. The outer radius, we said it's 7 minus 4. And the inner, it's 7, the axis of rotation, which is on top, minus the square root of x. And that's really the setup, how to do volumes, whether we're doing washers or discs. There is another method called shell method, and we'll go over, if not, I'll make a video based on that. But this is pretty much the setup. If you have any questions, you guys can contact me, and I can answer any of these questions. We'll have a couple of practice problems that I'll post on Schoology. Thank you.